Okay, so think about this. Something happens way out there on the sun, millions of miles away, right?
Yeah.
And almost instantly, it starts messing with your phone's GPS or disrupting satellite signals right here. How does that even work? How does that energy travel all that way and zap our tech?
That does sound pretty wild, doesn't it?
Sure.
But yeah, it's not sci-fi. That's space weather.
Space weather.
It's the sun's influence on us. And the sun, well, it's definitely not just a steady lamp up there. Its activity has these surprising direct links to the systems we really depend on.
Exactly. And that surprising connection, that's what we're diving into today. We've got some source material you shared, a couple of really interesting academic studies.
Right.
And our mission is to pull out the key takeaways,
Right.
about the sun's intense activity, sunspots, flares, that kind of thing, and really explore how they connect to Earth's upper atmosphere.
Yeah. And these sources, they give us a good look at how scientists actually study this stuff.
How they track those dark spots on the sun or analyze disturbances way, way up above us.
Exactly. The tools, the findings, and helps us piece together this complex interaction.
Okay, let's jump in then. The sun's active face. Usually the first thing people think of are sunspots.
Huh?
So what are these dark patches? Why are they important?
Right. So sunspots are basically temporary cooler spots on the sun's surface. They look dark just because they're not as bright as everything else around them.
Cooler, but important. Why?
Because they're caused by these intense magnetic fields, really strong concentrations of magnetism poking through the surface.
Ah, okay.
These fields are so strong, they actually hold back the normal flow of heat and energy from inside the sun. That's what makes them cooler.
So they're like magnetic knots, places where the energy is getting tangled.
That's a great way to think about it, yeah. And if you look closely, they have structure. There's the really dark center bit, the umbra, and then a lighter sort of filament-like area around it, the penumbra.
Okay. And you mentioned they're temporary, but they're not just random pops, are they? They follow patterns.
That's absolutely key. The sun has cycles. There's the famous one, roughly 11 years, where the number of spots goes up and down.
The sunspot cycle.
Yeah, and then there's a bigger one, about 22 years, the Hale cycle, where the sun's overall magnetic polarity flips. It really shows the sun is, well, variable.
Variables, right. Like that period, the Maunder minimum, what was it, 1600s?
1645 to 1717,
Wow. Yeah.
Decades with almost no sunspots. Really highlights how much activity can change.
Wow. Okay. And the sources mention scientists classify these spots different ways.
They do. There are classifications based on how they look, their complexity, like the Zurich classification, A through H usually.
A to H.
But maybe more importantly for predictions, there's classification based on their magnetic character.
Ah, the magnetic side again.
Yeah, the Mount Wilson classification. It looks at the magnetic polarities within a group like alpha, beta, gamma, delta. These tell you how mixed up and complex the magnetic fields are.
And complexity sounds like it might be important for explosions.
Exactly. Which brings us to solar flares, these sudden, really intense bursts of energy.
Intense is putting it mildly, based on the description here.
Oh, yeah. Flares are pretty much the most powerful explosions in the solar system.
Yeah.
They happen in those tangled magnetic regions around sunspots.
And the energy scale is just hard to grasp.
It really is. A single strong flare. It can release the energy of millions of 100 megaton hydrogen bombs all at once.
Million.
Or think of it like 10 million big volcanic eruptions happening simultaneously. It's enormous.
Okay, all that from tangled magnetic fields. The sources mention the first recorded one, Carrington, right? 1859.
Hampton Hodgson, yeah.
Yeah.
They actually saw a white light flare, which is rare, a major historical observation.
Yeah.
It really started people thinking about the sun-Earth connection.
And today, we classify them differently by X-rays.
Mostly, yes. Using satellites, like the GOES satellites, we measure their peak X-ray brightness. That gives us the C, M, and X classes.
CMX.
Yeah, each class is 10 times more powerful than the one before it. So C is relatively small, M is medium, and X flares are the really big ones, the ones that cause the most concern.
Okay, so we've got sunspots, magnetic, classified by looks and magnetism, and flares. Huge energy bursts, classified by X-ray power. Now, this is where that first study really digs in, right? Predicting which spots are likely to flare.
Exactly. That's the challenge. This study introduces a neat idea, flare production potential.
Flare production potential.
Basically a number trying to quantify how likely a certain type of sunspot group is to produce a flare. Super useful for space weather forecasting.
And the results are pretty stark, aren't they? It varies a lot.
Hugely. The study put numbers on it for those different Zurich classes, A through H, And, well, the simplest groups, like A-type, their potential is tiny, like 0.05 flares per group on average.
Okay, very low.
But then you get to the most complex ones, the F-type groups.
Yeah.
Their potential jumps to 2.18 flares per group.
Oh, that's orders of magnitude higher, from 0.05 to over 2.
Yeah, it's almost an exponential increase as the groups get more complex. D groups are 0.56, E groups 1.15. It just shoots up.
That's a massive difference. And there was a really key finding about where most flares actually come from.
Yes, this is critical. The study found something like 80% of all solar flares come from just 3 types of sunspot groups.
Just 3.
The big complex ones, D, E, and F classes.
80% from just those 3?
Meanwhile, the simpler ones, A, B, C, and H, they only account for about 21% combined. So if you want to predict flares, you absolutely need to watch those large, complex regions. They're the main players.
That really hammers home the idea that size and complexity, which means those tangled magnetic fields, are what drive flares.
Definitely. And the study backed this up statistically. They found a really, really strong correlation between the average area of a sunspot group and its flare production potential.
How strong?
Like correlation coefficient of 0.996, almost perfect. Statistically significant, too.
Wow. Okay, so size equals complexity equals flare potential, basically?
It strongly suggests that, yeah, it backs up the idea that complex magnetic structures store the energy needed for these big releases.
And if you just track the total number of flares over time, does it follow the sunspot cycle?
Generally, yes. The study showed that total flare counts tend to follow the patterns of sunspot numbers and total sunspot area. You often see those double peaks during a solar cycle in the flare data, too.
Double peaks?
Yeah, sometimes activity peaks, dips slightly, then peaks again within one cycle. It's a known feature. Though the study did note some slight differences in behavior between different flare classes or sunspot types when comparing different cycles, like cycle 23 versus 24. But the overall link is solid.
Okay, so spots, flares. But flares aren't the only thing the sun throws at us, right? There are CMEs.
Right, coronal mass ejections. These are different beasts. Not just a burst of light and energy, but actual stuff. Huge clouds, like bubbles, of plasma that's super hot ionized gas and magnetic field lines, blown out from the sun's corona, its outer atmosphere.
And they often happen with flares.
Often associated, yeah. They come from the same active regions.
Mm-hmm.
But you can have a flare without a CME, or a CME without a major flare. They're related but distinct.
And these CMEs, along with fast solar wind, are what really stir things up magnetically here at Earth.
That's usually the case for the biggest disturbances, yes. When a CME slams into Earth's magnetic field, our magnetosphere, it can trigger a geomagnetic storm.
Geomagnetic storm, okay.
And scientists track how strong these storms are using geomagnetic indices, things like KP, AP, DZT. They're just standard ways to measure how much Earth's magnetic field is being disturbed.
And the sources found a link here, too, between flares and these geomagnetic indices.
Yeah, they showed that over time, the total number of flares, like C plus M plus X flares combined, does correlate with these geomagnetic indices.
So it shows the whole chain.
Exactly. Magnetic tangle on the sun flare, maybe a CME travels through space, hits Earth biomagnetic activity, connects the dots.
Okay, now the second source, it shifts focus a bit. It looks at the direct effect of flares, specifically on our upper atmosphere, this ionosphere-thermosphere system.
Right, the IT system. This is a region way up, starting maybe 50 miles and going up hundreds more. It's incredibly hot, and importantly, it's electrically conductive.
Conductive because the sun's radiation ionizes the gas.
Precisely. Solar UV and X-rays knock electrons off the atoms and molecules up there. That creates the ionosphere part.
And why is this IT system so critical for us down here?
Because that's where a lot of our technology lives or passes through. Radio waves bounce off it for long-distance communication. GPS signals have to travel through it. So when that region gets disturbed by solar activity, it can really mess with those signals, disrupt communications, mess up GPS accuracy, navigation, stuff like that.
Which is why scientists measure something called TEC, total electron content.
Exactly. TEC is a really key measurement. Satellites, especially GPS or GNSS satellites, send signals down. As those signals pass through the ionosphere, they get delayed slightly by all those free electrons.
Oh, okay.
By measuring that delay, scientists can figure out the total number of electrons along the signal's path. That's the TEC. Changes in TEC tell you directly how the ionosphere is changing.
And the second study used TEC to look at a specific flare.
Yes, they did a case study. They investigated how the IT system responded to one particular flare an X1.3 class flare.
An X class, so a pretty big one.
Decent size, yeah.
Yeah.
But the important thing was when it happened. They specifically picked one that occurred during a time of low geomagnetic activity.
Ah, trying to isolate the flares effect, separate it from a general geomagnetic storm.
Exactly. They wanted to see what the flare's radiation itself did to the atmosphere without the complicating factor of a big CME hitting at the same time.
Clever. And what did they find? Did the flare have a direct impact?
Yes, it did. That was the main finding. The flare definitely induced disturbances in the IT system.
Yeah.
They could see these sort of periodic changes like waves rippling through the tech data.
Okay, so direct impact confirmed.
Right
Proof
on.
positive.
Proof positive. But there was a nuance, a really interesting one.
Yeah.
Even though geomagnetic activity was low, the study concluded that Earth's background magnetic field still influenced how big those disturbances were and how long they lasted.
Wait, even during quiet times, the magnetic field still played a role.
It seems so. It suggests it's not just about the flare energy hitting the atmosphere. It's about how that energy interacts with the existing magnetic conditions, even the quiet ones. Adds a layer of complexity.
That is subtle. So understanding this requires some pretty heavy-duty tools, I imagine. Models.
Oh, absolutely. Scientists use complex computer models like global circulation models, or GCMs, specifically designed for the upper atmosphere. GITM was one mentioned.
Right.
These models try to simulate the physics and chemistry up there and how the IT system responds to inputs, like the radiation from a solar flare.
And they feed these models with other data.
Yeah, they need inputs, like models that estimate the flare's radiation across different wavelengths, FISM2 was mentioned, and models for the background atmospheric conditions. Sometimes they even use real-time data from satellites to fine-tune the models. One source mentioned using data from the Grace of the satellites for that.
It's amazing, isn't it? Using satellites to help model the very phenomena that can disrupt those satellites.
It's a necessary feedback loop.
The sources also gave a nice little historical tour of how we figured all this out. It wasn't obvious, was it, what's going on hundreds of miles up?
Not at all. It goes way back. Like 1839, Carl Friedrich Gauss suggesting electric currents high up just based on magnetic field variations measured on the ground.
And then Balfour Stewart, 1880s, he proposed a conductive layer driven by winds interacting with the magnetic field.
Yeah, and he even used the term magnetic weather. How about that?
Wow, way ahead of his time.
Definitely a precursor to space weather. Then, early 20th century, you had the puzzle of radio waves. How could they travel so far?
Right, Marconi and all that.
People theorized about reflection off an atmospheric layer. But other ideas, like waves just bending along the surface, were popular for a while, even though they didn't perfectly fit the observations.
Until Sidney Chapman came along in the 1930s.
Chapman's work was foundational. He was the one who really theorized that the sun's ultraviolet light was the key. It ionized the upper air, creating what he named the ionosphere.
And he figured out the layering, too, how different wavelengths get absorbed at different heights.
Exactly. That explained the different layers, D, E, F regions, that radio experiments were starting to detect.
And then World War II, suddenly understanding the ionosphere became really important.
Hugely important for radio communication, for radar. It pushed research forward massively. Lots of data was collected, even if kept secret initially.
And then the space age really opened things up.
Oh, completely. The International Geophysical Year, 1957-58.
Yeah.
And then Sputnik Explorer 1, getting instruments up there.
Direct measurements. In situ.
Total game changer. It wasn't just about the ionosphere anymore. It broadened into aeronomy, studying the whole upper atmosphere, neutral parts included, which leads us to where we are now.
Right, to today, where space weather is this vital field using these incredibly complex models and satellite data we just talked about.
Trying to predict and understand these effects to protect our technology.
Okay, let's try and tie all these threads together for you, the listener. We started way out at the sun, looking at sunspots.
Those tangled magnetic regions, classified by complexity and magnetic structure.
And saw how the most complex ones are responsible for the vast majority of solar flares, those huge bursts of energy.
Flares, and often those big eruptions of material, the CMEs.
Which then travel to Earth and can cause geomagnetic storms, disturbances in our planet's magnetic field that we measure with indices.
Right, but we also saw, thanks to that second study, that flares have a direct impact too.
Hitting our upper atmosphere, that critical ionosphere-thermosphere layer.
Yeah, causing disturbances like those waves seen in the tech data, even when there isn't a big geomagnetic storm going on.
And finding that even Earth's quiet background magnetic field seems to play a role in how those disturbances evolve.
It really paints a picture of this deeply interconnected system, doesn't it? From the sun's visible surface right up to hundreds of miles above our heads.
All these links spots to flares, flares to CMEs, CMEs to storms, flares directly to the ionosphere. Understanding them is key. Key to predicting space weather and its impacts.
From Gauss wondering about currents in the sky, to using supercomputers and satellites like GRACIFO to model flare impacts. It's been quite a journey of discovery.
So here's a final thought to leave you with. We rely so incredibly much on satellites now. GPS, communication, weather, just about everything.
Our modern lives are built on it, really.
So knowing what we now know about how profoundly and sometimes subtly the sun influences that critical region where these satellites operate, what does that tell us about the future? How much more important does space weather forecasting become?
And maybe, how much more prepared do we need to be for the whims of our nearest star? It's beautiful, it gives us life, but it can also be incredibly disruptive. Something to think about.